estimators. In this talk, I try to use the derivations of jumps to get the guaranteed estimation for the isolated semigraphs. This is joint work with Yulin Song, is my students. I have separate 5 parts to introduce my work. The aim is to get the following 2 type equations estimation. Here is not partial differential, but it is the additional differential equation. This is only Levy process, not without jump, without diffusion. And this is multiple noise. Here we assume B is bounded, is measurable, and LT is a pure jump Levy measure with a character measure. The measure is infinite. We try to get the estimate of the constitute this estimate. Then the strong follow property and Hannock equality is flows. Since we try to use the derivatives, there's a lot of work in this aspect. Here we list some of them. The 2 process, maybe there's I lost a lot of others' work. This firstly is based from 1986. He used the derivative get the iteration by parts formula for pure process. In his case, his character measure is Lake measure. We know we consider the general character measure. And also noise is consider the not Lebesgue measure but local regular Levy measure. Recently, Feng Yuan in these 2 years get some linear SPDs estimated, and he's for the linear SPDE. And I want to extend all results to the general SDE with the general Levy character measure. The basic assumption is we assume the character measure has a density on the small space. Here, this is this space is Rn ordered space without 0 point. The character measure is loaded on this. He has a density with this density is positive. In general, this is the infinite measure. And the derivative, we will take derivation. The derivative V is a predictable process. His support on this space as a T under Z suffixation, his support on this space, on this domain, and the second derivative is continuous. Also, for the both evidence, he is bounded. Now we follow the previous works, introduce the derivative. Firstly, we give a perturbated random measure n epsilon. It's just like this. This is the direction, the jump direction. The base gives the definition of this kind. For a fractional jump process, if he have a LP derivative, if there is a variable, raw-down variable, which is LP integrable, and this limiter exists, then this is called the LP derivative. Based on the character measure density, we can introduce this lambda epsilon, and from lambda epsilon we can introduce this zt, and from here we can introduce a new property measure p epsilon, and which is absolutely continuous with original property with a density zt, and this is the true property measure, since we have the two lemma. First one, this z1 epsilon and zt epsilon minus 1 is our epsilon is uniformly integratable, and from this theory, from the Naris in 1988, the p epsilon and p has the same law as respond to the n epsilon and nt. This is the original jump process. This is the new jump process. And it can be shown that under the direction of the v, if we satisfy the original with the condition, we give the condition, then the fractional has L1 derivative, and he has this integral by part from a host. And RT is given by the direction v and the density of the character measure in U0. And we can extend this definition to the diffusion plus jump case, and the results is similar. Firstly, we set the filtration generated by Bloom motion, and another one is by Poisson process, by the Levy process, and we assume these two filtrations are independent. And if we take H from this space, n space, which one is exponential integrable, and we satisfy the condition H2.1, then this Kant variable can introduce the new property measure Q epsilon, which is a truly property measure, and he has this relation with P, with the original property P. Also, we can similar definite the fractional depend on Bloom motion and the Levy process, and if there is a fraction, there is a variable satisfy which is LP integrable. If this condition, if this is satisfied, we call this one is the LP derivative of the F. Although this is a general definition, but in the later we cannot use this. Also, you can get the proposition 2.4. If H is satisfies the given space, and V, the direction H and V satisfies H 2.1, then the fractional of Bloom motion and the Levy process has a L1 derivative, and similar, the derivative formula is just like this. Here is the Bernoulli motion part, and here is the Levy part. Also, there's a lot of derivative according to the jump part, but this kind of definition can combine the Bernoulli motion case and the jump case. Here, if h is 0, it's a poor jump case, and if no Poisson part, your Levy part is just a Malone calculus. So next, we want to show this. We want to consider this additive equation has considers the estimation, granted estimation according to this process, and then next we can do the. This is the additive jump process. Here, the LT is only jump part, not without the Bernoulli motion, and B satisfies the Lipschitz condition. In generally, this condition has a unique solution. It can be right here, like this. Under how axis 3. Okay, how about figure 3? No, here. We need introduce a new hypothesis. Suppose the direction derivative along this direction. This direction is bounded by two separate factions, and K is measurable fraction, and H is L1 and L2 integrable on space U. Then the given equation has a derivative according direction V, and he has these forms. There is a point measure, not a Young measure, not a Levy-Young measure. Next, we assume under this assume if the density of the jump of the countermeasure and the direction of the derivative such is bounded by a fraction phi and psi is control, then Norris in 1983 gets this result. This is a Norris result. He's depend on the Levy countermeasure, but here is depend on the general measure. The idea is the same. So I think this is just a little change of the original. This is integral by part, and for getting the granted estimation, we need introduce give some restriction on the countermeasure. This countermeasure, if the countermeasure is infinity as epsilon go to 0, this is infinity, and this is infinity. Though I think suppose this is finite. This is finite. This means if this is finite measure, this doesn't exist, but only this is infinite measure. This has mean, and also we take the direction from this space. Then we can get the granted estimate. Here is B is original B is bounded has two derivatives, and assume theta is finite. Then for bigger t, the estimation holds. From here, you can get from this formula. It is easy to get this PDE strong failure. here this condition is basically is fundamental. If this is infinite, is finite, this condition, this will be not exist. It's infinite. This is just infinite. Yes, it's equal to minus infinite. The proof is use the idea of the Monk calculus. We want to get this estimate, and this estimate, if say is assume this is has one derivative, and then this equality, this one is equally this derivative, and this is the Jacobi equation from the original equation. And another, we can take the derivative from the original equation. From the original equation and this one, by using the variation of constant formula, we can get this equation. And if we take the direction as this, then the duration has this form, and this is noted by ht. Then, if ht is positive, almost sure, then this formula can be right. Jt is here. Under some condition, you can show this is almost sure. It's almostly finite. And this greatest, this one can be replaced by this one. And this is a take derivative here, takes the first. And this is a derivative. We take this derivative, this formula is from here. And then take gt, gt is the outside. You can get this formula. Here, this is just a if you control, this is finite. This is finite in L1 or L2. In L1 or L2, finite. Then you can get this estimation. Here is the two lemmas. First one is also from Norris. If this is for any t bigger than this one, so you will see this is a master infinite measure. Then he has at p for any p bigger one, this is integrable. So h is almost sure positive from this lemma. Also, you can get more. You get exponential integrable. This one. Also, you can and use this under these conditions. You can get this exponented finite. Is controlled by this one. From this lemma, you know this one is finite. You can write this is finite. Then we get the you can get this formula. This equation contains a concrete example. For example, if we take rho is unstable the density from the symmetric stable process, unstable process, then we can check the u1, u2 as this can, and take two fractions phi and psi. From these two fractions, you can get the derivative fraction is like this. And all these conditions, the theorem 3.5 is hold. Thus, we can get the estimation of the multiple additive jump process, the equation derived by the additive jump equations, the semigroups, the estimation. For getting the others inequality, we need added some restriction on the space. Here, based on original H rule, this term is needed. So, under this construction, use the granted estimation. It's not difficult to get the Young equality, just like this. Also, this is the basic condition. And Hank inequality. This for this these two kind inequality, this Young equality and Hank equality and gradient equality is obtained in the additive jump case by the Feng Yuwang, maybe other people, but he used the derivative and coupling. I think in this method, without use coupling, just use the derivative, it is enough. Coupling, yeah. For the multiple jump case, this result can be obtained similarly, but here coupling methods is difficult to use, but only use the derivative. I think this shows is enough also. But the difference is this method is not okay. I think this one this is not concrete as if you use the coupling, this is concrete. This is better, looks better. But in the since this is only use derivative, so this look long, but not better. So let's see how to get this. Now we consider this multiplicative equation, jump equation case. And here f is measurable, b is assume this is has a unique equation. For example, is L2 is bounded have a two derivative, and is Lipschitz and it is it doesn't matter. Okay, here b is and we assume f the diffusion part, the jump part has this kind condition. He is bounded on for the first derivative and for the second derivative and for the first two derivative. And also the super is L2 incredible. And the direction, the derivative direction is bounded by the two separate fraction, and also this is bounded, and this has a continuous bounded fraction and add up to 4 integrable. But this condition may be too complex. Under these conditions, the equation has a derivative, has L2 derivative, and the derivative is just this is a diffusion part, this is a jump part, and this is from the derivative, just promotion, just like promotion. There's a Poisson point process and a Poisson Levy measure, and we set MF is a derivative 1 plus f for the first derivative over f1. We assume this is finite as a function s and zeta, and also give a classes G. If H, we assume H belongs to G. This is no general condition. You can say if this is general for the this is the usual condition for the jump case, the jumped equation. From this condition, the Jacobi equation exists, and there's an inverse matrix is like this one. And if the H 4.1 to 4.2 and H 4.5 holds, then the two equation has a unique solution. And with this condition, the estimate is also getted from this bounded. This is bounded. Yes, and also this is a strong failure from this equation. And the proof is similar to the additive case. For the additive case, here you can get the derivative along the given direction v. This since it's a multiple case, so this derivative is a complex. But if you take the duration, v is this kind, then also you can get this derivative is equal to h1, h2. This is a number that depend t plus this Jacobi, and other step is similar to the additive case. Also, if the jump process is a symmetric unstable process, and the density is this one, you can choose suitable U1, U2, and and the direct fraction. All this just like this one. All the conditions above the theorem is all satisfied, and you can get the estimate, granted estimate. For getting the Young and Hank inequality, we need use the added other direction on the direction choice. For choice direction, you need H. You need to satisfy this condition. Expect this one, and also you need this one. And under this condition, under this direction, the Young equality just is held also, and Hank inequality is obtained just like this one. All these three part is depend on this is infinite. But if this is finite, all the result false. But instead consider original group, we can consider this group is a jump part is bigger than 1, and this is also is a new group. This group was considered also by Feng Yuan. He considers a linear case or the additive case. For the general case, this is also can be considered, and use the same results. We can get this is estimate is also still hold, but and this is optional. I don't know what use this and others and others. This kind of semigroup, what use in the other place? But this is a property, just property. And this is guaranteed estimate. And also, this is Hank for P1 is Hank estimate. And this is granted. This granted. This is for the additive jump process. This is Hank process. And this is the additive granted estimate. And for the multiplicative, you also get this granted estimate. And also, I have not write the other Young and Haneke inequality still holds. I have not write here. Thank you.
Questions, comments?
You have a formula for the gradient of the semigroup, and there is a constant depending on t. For instance, in your example of alpha stable, one can make this constant more explicit. So there should be a constant depending on alpha in your example. It should be 1 over t, 1 over alpha if alpha is greater than 1. You can do this. So you can...
No, I have no concrete. I just check the condition. Has not write read clearly. I not read.
Any more questions? I think no. So thank you, the speaker, very much, and thank you everybody who gave the talk this morning. And remind that we meet at 2 o'clock. Who is interested in Fokker-Planck and Kolmogorov equations. And later there are talks from 3:10.